my name is Raj, and today I'm going to talk to you today about natural language media search in Elixir, Bumblebee, and Nx. So this is my first Elixir conference. I work as a software engineer at NVIDIA, where I work with Elixir and Phoenix. I started my journey in software engineering with React and TypeScript. I built and broke a lot of web apps in React, and I've also dabbled a bit with Python. I write about the things I do in the form of blog posts, which can be found on my website. And these days, I'm also learning more in machine learning through Elixir. Next, about InVideo. InVideo is a web-based video creator and editor tool. And with thousands of expertly made templates, it's the fastest way to create publish-worthy videos right from your browser. And this year, we are launching a new product which will allow users to create entire polished videos complete with voiceovers and all the relevant media just from an idea. And for this, we have adopted Elixir for our backend services. And we are loving Elixir, and we are using Phoenix framework very heavily. And more recently, we are also adopting the Bumblebee and the entire machine learning ecosystem in Elixir as well. So, all right, so what is the goal of this talk? The main goal of this talk is to get you up and running with Nx, Axon, and Bumblebee in Elixir, and basically get an overall idea of utilizing it for a real world use case. We are not going to go in depth in terms of the machine learning topics. We are just going to get enough context of those to get us started. And once you're comfortable with getting something like this to work, you can easily expand on that knowledge and go deeper as and when it is required. So the first goal of the talk is to understand the fundamentals of these libraries, understand the purpose of each of them, and how they come together in allowing us to achieve machine learning tasks in Elixir. And for the second goal of utilizing these for a real world use case, we are going to take a look at building a simple natural language media search using the CLIP model by OpenAI to explore this. Of course, due to time constraints, we won't build the entire app step by step in this talk, but we'll focus on the main concepts involved in this. So before we actually start, let's take a quick look at what we are trying to build here, right? We are trying to build natural language image search. So generally, image search is done using the associated text metadata of the image. And most of the times, it's not enough, right? Let me show you an example. This app that we are trying to build, the images which are there in the dataset right now, they are taken from the free Unsplash 25,000 image dataset. So all of these are on Unsplash, right? Using the search that we are going to build, let me try to search something like a dog in a red SUV. Okay. So if you can see, we got exactly what we wanted. This is exactly what we wanted. And I have this image over here on Unsplash. So if you can see, this image is actually there on Unsplash. But if I go here and I search on Unsplash, a dog in a red SUV, you can see that the results that we are getting there are not very accurate, right? Because the search that happens there is via text, but the search that we are building, it has an actual understanding of what's going on in the image, right? So we can, just to again give you a bit of a sneak peek, we can do things like photo of a dog with green trees in the background, and it got what I said. If I just do orange trees in the background, it basically got what is happening in the image. So what we'll do is we'll try to work our way up to understanding what is happening here and how this works. To start off with, we'll try to understand the different libraries. So there's three major libraries related to this machine learning in Elixir: Nx, Axon, and Bumblebee. Of course, there's many more ML related libraries, but these are the major ones that you're most likely going to use. First off is Nx, Numerical Elixir. It's a library for creating and manipulating multi-dimensional arrays. It's intended to serve as the core of numerical computing and data science in the Elixir ecosystem. Actually, if you're coming from the Python ML ecosystem, this will kind of remind you of NumPy. And while the basic purpose is kind of similar, there are a lot of differences due to language constructs like immutability, for example. Right? And at the core of Nx is Nx Tensor. Okay. So Nx Tensor is the main data structure that the Nx library is basically designed to manipulate. All the other functionality that NX provides is just built on top of the implementations of NX Tensor behavior. We'll try to understand the fundamentals of NX Tensor because this will help us definitely. So NX Tensor has 4 key fields: data, shape, type, and names, right? First up is data. It contains the actual data, which is the tensor's value. And one thing that's important to note here is that the tensor's data, it's just a flat VM binary, okay, which is just an array of bytes. So on the right-hand side, even if you see in the io.inspec, you see it as a list of lists. That is just how it is printed. In actuality, it's just raw bytes, and they represent the individual value in the tensor, right? So as they're stored in the flat container, NX does not operate on lists or nested lists. It just operates on flat raw C byte arrays. And because of which it is able to perform very efficient operations, even on very large tensors, right? This definitely gives us a performance boost, but that also means that we need another field to store the metadata related to what data is where and how to interpret the raw byte data. That is where the type field comes in. So the type is represented as a tuple of the type atom and the associated size with it. For your reference, these are the typical valid types and valid sizes: float, floating point, signed integer, unsigned integer, brain floating point types as well. The size actually accurately describes its precision, right? So if you're going for a 64-bit types, it's going to consume more memory. It's going to be a bit slower, but they are going to be more precise than the 32-bit counterparts. Next field is the shape of the NX tensor. This is related to the nested list representation that you see for a tensor. And a tensor shape is the size of each of their dimensions, right? So for example, the tensor that you see here, if you visualize it as a 2-dimensional matrix, it has 2 rows and 3 columns. So the shape is 2, 3. Finally, tensors can also have names for each dimension, which is helpful for us to be explicit about what dimension we want to perform a specific operation on. Right? For our use case, to just get you started, one last thing that you need to know about NX is that it supports pluggable backends, which means that NX is designed to work with different backends for performing tensor computations. And this also means that you can switch between different implementations of the actual underlying tensor operations without changing your code. So NX just provides you consistent API for working with tensors, and the actual computations are delegated to the backend of your choice. So for example, you might have a CPU-based backend for running computations on your local machine and a GPU-based backend for working in a production GPU-equipped machine, right? This allows us to switch between these different environments without even changing your Elixir code. Right now, NX supports these 2 accelerated backends, EXLA and TorchX. By default, it comes with the binary backend. If you don't set a backend, then NX is going to use the default one. But as you can see, the default one is very slow compared to the accelerated backends, EXLA and TorchX. The matrix multiplication of this size, the default will take around 32 seconds, whereas EXLA CPU backend just takes 1.3 milliseconds. So if you're playing around with NX and you discover that things are taking too long, you might want to check if you have set the correct backend. We'll see how to configure this in backend in some time. So that's a brief introduction to the NX library. Next, we are going to take a look at Axon library. Right? So it is a high-level interface for creating neural network models. It is actually built on top of the NX library. And so a neural network, right? It's made up of different layers. And with Axon, we can define these layers of a neural network as composable functions. And Axon provides a lot of functionality to create and manipulate neural network models. But for our use case, we are going to use 3 functions, which are listed here. We'll understand what these do when we come across them later. Right? Finally, Bumblebee. It's a library which is now built on top of Axon, right? And it's designed to simplify the process of loading your pre-trained models from a model repository, right? Like Hugging Face, for example. It also provides us ready configurable Axon models for things like vision. We have the ResNet model for image classification, diffusion. Bumblebee supports stable diffusion image generation model. Text, there's GPT-2 text generation and a lot of text classification models as well. There's also audio. Right? Recently, the Whisper model for speech to text is also supported by Bumblebee. In our case, we are going to use the multimodal clip model that Bumblebee provides to build our media search demo application. So let's take a look at the actual clip model and try to understand it, what it does. Clip stands for contrastive language image pre-training. And as the name suggests, it's a model that learns to generate meaningful representations for both images and texts. It was trained on large data sets of images and their associated text descriptions. So during the training process, the model learned to associate the right text with the right images by comparing them. And the main idea behind Clip is to bring images and text into a joint embedding space, right? Where semantically similar images and semantically similar text, they are close together in that embedding space, right? Practically speaking, the clip model allows us to convert a given text into its vector representation. So now a vector is basically a list of floats, okay? You can think of it as a single row tensor of size n, right? The Nx tensor that we just saw. Similarly, you can also convert an image into its vector representation, right? Clip has a component of the model called clip text, which helps us get the text vector. And it has another component called clip vision, which helps us get the image vector, right? But one key point to note here is that these different vectors, text and image vector that we get, they are in their own different space, right? They are in their own dimensionality. They can't be compared easily with each other. Like even if you compare, the result will make no sense, right? But the great thing about Clip is that it is multimodal, right? It enables us to project these different text and image vectors into the same dimensional space. This is done using the text projection and visual projection layers that the multimodal model provides us. And now, once these vectors are projected in the same embedding, same dimensionality, we can say that the vectors which are closer to each other are similar to each other. They might be two image vectors or an image vector and a text vector. We can say that they are similar to each other if they are, the similarity is same or even closer. And this similarity is calculated using cosine similarity. Basically, if you imagine you have one vector and another vector, if they are normalized vectors, then the dot product of these two vectors will give you the cosine similarity, right? The cosine angle between the two vectors. So that is the background info that we need to basically put this all together. I hope you got the overall idea of what does what. And now, okay, how to put this together? Okay, so to put this all together, this is our plan. We will take an image, first get the vision vector of it from the vision model, and then project that into the joint embedding space. And once we do that, we'll get our final image vector that we can say this vector represents this particular image. We'll do this for a number of images, right? So we'll have n image vectors. Okay. Let's imagine that we store these different n image vectors into a file, and then we can load them in memory whenever we want. Okay. Next, we will take a text. Let's say, for example, the words two dogs, right? Then we'll convert that into a vector using the text model. Then again, project that into the same latent space, and that will be our vector that we can say represents the text that we have given it. After that, all we need to do is calculate the closest image vectors for a given text vector. Okay. And the images that correspond to those closest image vectors will be our search results for the query that we have entered. So there are two questions that arise over here, right? How to store a bunch of vectors in a file, and then how to calculate the nearest vectors among those vectors for a given query vector. The answer to those questions is the HNSW library. Okay. HNSW is the name of an algorithm for performing vector similarity search. And this library allows us to use that in Elixir. Originally, it's a C++ library, but there is a Elixir binding available for it that just works directly with Nx tensors. There are similar libraries as well, like NI or FES. And there's even full-fledged vector databases like VV8, Pinecone, pgvector that support many more features. But for our use case, this is HNSW lab is going to be more than sufficient. You can check out annbenchmarks.com to see how these different libraries compare with each other. Right? Okay, so time for some actual code now. First off, these are we will install the libraries that we need. On top is Bumblebee, Nx, Xla, the backend that we'll use. Then we have STB image, which is a library that will allow us to read and load a image file. And finally, the HNSW library that we just talked about for similarity search. Okay. Next, as discussed before, we'll set the Nx backend to Xla. This will help speed up tensor operations. Adding this line in your config.exs file will set the default Nx backend to Xla. Right. So after this, we'll focus on first 2 points in our plan. First one is getting a vector from a given text, and the second one is getting a vector from a given image. Okay. These vectors will be projected vectors that we can compare with each other. Once we understand how to do these two things, the rest of it is pretty much wiring stuff in wiring with Phoenix, LiveView, etc. So to start off, let's see how we can get the text vector. First, we'll load the clip model. There are, as we discussed, 3 components of the clip model. First is the multimodal clip, which is the model for text to image similarity. Then we have clip text and clip vision. Okay. So we are using Bumblebee's load model function, which loads a pre-trained model from the model repository, which is Hugging Face in our case. The module option specifies the model specification module. If it is not specified, it is inferred from the model's configuration file. In case of clip, if you don't specify the module, the multimodal model gets loaded. Okay. Why do we need the multimodal model? So that is the model that contains the necessary parameters needed for the actual projection of text and image vectors into the same dimensional space. Okay. Next step. As discussed, we can't use the loaded clip text model directly. We need to manipulate it to create an updated model that will give us the final projected vector that we can actually use. For this, the first thing that we need to do is take that model, update it to extract the pooled state. Okay. Now, what is a pooled state? Any neural network like clip, there are different layers. The input that you give goes through the series of those layers, and pooled state is the compact representation of the input that retains most of its important features. For text, you can imagine that it is a representation that captures the overall meaning of the text. Okay. And to extract these pooled states, you can see we are using accent.nx. Let's see what accent.nx does. It takes in an accent model and a nx expression, which is just a function, and applies the nx expression to the input data when the model is used. In our case, the line that you see highlighted over here, it is used to create a new layer in the model that applies the function to extract the pool state attribute from the output of the previous one, which is a text model. And the anonymous function that you see passed in is a nx expression function that takes the output of the previous layer and returns the pool state attribute to the next layer. So now we have the raw text vector, but the projection is remaining. So we need to update the model to add a dense layer for doing this projection. Now the question is, what is a dense layer? In neural networks, a dense layer is basically a fully connected layer where each neuron in the layer is connected to all the neurons in the previous layer and all the neurons in the next layer. And the primary function of this dense layer is to learn and output a weighted combination of its input features. And in our case, this dense layer is used to project the features extracted from the text and later the vision models into a common space. So with this, our model for getting final text vector is ready. We just had to add 2 layers. First is to extract the pool state, and second one is a dense layer to do the final projection. Cool. Yeah. Now, when you apply a neural network model to some input, you give it some params, right? Params are basically the weights for each layer that it has to apply to the input data. So if we were using a simple text model above, we would have just used the text params provided. But in our updated model, we have an extra layer for text projection, right? So in the params that we give, we will need to include the params for text projection as well. Those we can get from the multimodal params that we got when we loaded the clip model before. So now with this, we have our final model and params that we can use for a given input. So how to use it now? So now is the time to use those final model and final params. We'll use it by using accent.predict to get the output from the input text. But now the input for the model is not going to be a text string, right? It will be the tokens of that text. So we load the tokenizer that the clip model provides us, apply the tokenizer to the text, and use the tokenizer output with accent.predict along with the model and params. If you're wondering what is this tokenizer doing, tokenizer is responsible for converting a raw text, which is two dogs in this case, into a numerical format that can be processed by the model. So we can't feed text directly to the model. We use the tokenizer provided to us by Clip. Then accent.predict. Let's take a look at what accent.predict does. It processes the input data through the model's layers. It applies the parameters that we have given, and the parameter, again, they are essentially the weights and biases of the model. And finally, it computes the output values for each input. Here, as you can see, we are using the same accent.predict, and the model and the params are our updated text model and projection head, and the params are text params with the projection that we created earlier. The output that we get from here is the final text vector we need in the form of Nx tensor, right? Let's try to actually run this. I have a file which does the same thing with the code that we saw. It installs the dependencies, loads the model, then applies those two steps. First is getting the pool states, then a dense layer, and finally uses accent.predict and prints the output. All right. So let's just try to run it. Getting text vector demo. So you can see it is now loading the model. It loaded the model, and now it is loading the tokenizer. And finally, we have the tensor. And this vector, which, as I said, is a list of floating points, represents the text that we have given it. Right? Similarly, at this point, we are getting a vector for text. Doing this for image is also very similar. We initialize the clip vision and multimodal models, update the model to extract pool state. Now, then update it again to add the dense layer for visual projection this time, add the params for the new layer we had. One thing that's changed here is that we'll read the image binary data using STB image library, which will basically decode the image and extract data about the shape type, etc. Finally, we load the featureizer here. For text, we use tokenizer as the pre-processing step, but here we are using the featureizer. Featureizer is responsible for pre-processing the image data into, again, a numerical format that clip vision model can work with. And then lastly, we'll use accent.predict with the updated model and the params to get the output image vector. Let's take a look at that as well. It's there in the file getting image vector demo. Same thing, install all the dependencies, load the vision model, the multimodal params, then create an updated model projection head. We have the getting the pool state, then visual projection. Finally, put the visual projection params to get the updated params. Then use STB image to read the file. So the file here is this one. I'll just show the image. This is the image file that we are loading. Then we are using STB image to decode it, putting it in the featureizer, and then the featureizer output will be the input for our model that we just created. Let's try to run this as well. It's again loading the whole model, loading the tokenizer, and then converting it into the tensor. Yeah, this is the tensor that we got for finally our image. So these two tensors, they can be compared with each other, and that comparison will give us how similar they are to each other, right? Okay, so now that we know how to get vectors out of image and out of text, but as you saw, loading the model takes some time, right? It doesn't make sense to load model every time we want to run inference in a production app. For our demo app, we are simply going to load it once at application start and store it as a reference in an agent. But for production grade apps, one should use nx.serving, right? Which provides you a way to batch multiple requests coming in for inference, and it really speeds up things. Now that we have the ability to get vectors out of images and text, next thing remaining is, so we'll create a vectors of multiple images, just whatever we did for one, do it for n, which will be our data set of the images, okay? And then create the HNSW index with those. This part is actually really simple. As you can see here, the tensors is a list of vectors of multiple images. Then while creating the index, we just need to specify the space, which is cosine for us, the dimension, which is 512 for us, and finally the max number of elements you want to store in that index. And then we add each of the tensor to the index, and finally store it and save it to a file. Later on, we can simply load that index and use it. Right? How will we use it? Right? That is the question. So we are creating the index to query the nearest image vectors to a given text vector. Okay. Doing that is also very straightforward. We use the knn query function. We pass in the created index, the query tensor, and just say how many results we want out of it. Right? This way, we'll get an array index of the most similar image vectors of the query vector that we have passed in. Right? So we have taken a look at the main parts of building the demo app, which is getting vectors out of image and text using Bumblebee, Axon, Nx, and the clip model from OpenAI. Then storing those vectors in a HNSW index, and finally querying it to get the nearest vectors. Right? After this, the next steps are just wiring it all up. I'll give a brief overview of what it involves. Basically, wiring in the vectorization logic, initializing the model at application start, storing its reference in an agent, and then integrating that with Phoenix, creating a live view UI on top of it. And finally, just writing a script for indexing a lot of images at once. You can use any images you want. For the demo, I've used the 25,000 image dataset that Unsplash provides. Yeah, so we'll just go again to the demo app. And hopefully now when we are doing this, we will understand what is happening underneath, right? I'll just try some search queries. Let's say coconut tree from above. So it understood what we are trying to do, and it gave the coconut view of a coconut tree from above. If I just say coconut tree from below, yeah, it again gave the images that it had for from below, right? One more, let's say dogs playing in snow. We get exactly what we wanted. If you say dogs playing in the sun, again, we get what we wanted, right? I've hosted this app on Fly if you want to play with it. The code for it is also open source. You can access it on this URL. And if you see the repo over here, yeah, this is the repo. It has the installation instructions, also the instructions if you want to use it with your own images or with the sample dataset. I've also included a link to the pre-built index files for the 25,000 images so that you don't have to spend time doing that. And yeah, you can also use your own images and index those if you want. That's it from my side. Thank you so much. If you have any questions about this, would like to get in touch, feel free to contact me on Twitter. I hope this was helpful. That's all. Thank you.
Hey Raj, that was an awesome session. I've always wondered how to integrate like an image processing library into live view. So to have an idea of how to do it now is pretty awesome. I'm looking through the questions and I can't see any at the moment. So if you have a question, please post it in the chat. We can take the next 7 minutes, I believe, to answer these questions. But in the meantime, Raj, I think since there's no question, you can maybe talk about something. Yeah, or maybe if there's a part of the talk that you wanted to explain a bit further that you didn't get time, now is the time.
Yeah, sure. So if someone wants to get into really understand how this is working, I've created a list of blog posts and basically some links that will really help them. Yeah, I started at this as a beginner, and big props to Dockyard and the blogs that they run. That was very helpful. Yeah, that's all. I just wanted to share this. This will be helpful for people who are just getting started.
Awesome. So we have one question from Varun. I hope I pronounced that name correctly. So he asks, or she asks, should we use HNSW index or go with a managed vector database solution for saving vectors?
Oh, okay. That's a great question. So yeah, that depends on your requirement, right? Like let's say if you have a couple of 100,000 vectors, then an HNSW index will probably run fine. But if you just want, if you have a list of images or if you have vectors that you have it already, then you can create the index beforehand and just use that. But if you have more requirements, for example, one of the requirements that we had was, let's say you have different sources of image, right? You have different providers, right? And then you want to filter those images that I only want to get search results out of one particular category. In that case, you probably would need more than just an HNSW index. You can use VV8, which provides a pre-filter, right? So before actually running the inference, it will only run the inference, which is the compute heavy part, on only the images which match that particular filter for you. Or for example, if you have a requirement that you want to ingest images at runtime, if you're using user uploaded images, then you can't use HNSW index directly, because it creates, it creates a file and you'll have to figure out yourself. But in that case, a VV8 or Pinecone, that kind of vector databases will probably be the way to go. I hope I've answered your question.
Yeah. I believe he can comment in the chat, but so far so good. There's actually a follow-up question. Is something like this possible for videos as well? It would be cool to search video using natural language. And actually, I'm curious myself. So is something like this possible also for example, music files? Think of, for example, Shazam.
Yeah. So, okay, I'll take the videos one at first. If you want to use the same model, right, the clip model, let's see, what is a video really, right? A video is just a series of frames bounded together, right? So what you can do if you want to implement this for videos is probably take some keyframes out of the videos. You can use FFmpeg to detect when the scene changes in a video, and you'll have a set of images which correspond to a particular video, and you can run the same process that we just saw. You'll get a result in images, but you can probably map a image to a video and then return the video as the result. So if I'm saying dogs playing in snow, I'll get the image associated with it, but I know that this image I've taken from this video, and then I'll show the video to the user. So yeah, it is definitely possible for a video.
Great.
And second one regarding audio, right? So with this model, it's not possible. But if there's a model called audio clip, there's a great research paper on it as well. So what they did was, over here, if you see, they have associated images with text, right? What the authors of audio clip did is they associated audio with the associated text descriptions. So that is also a multimodal model. So they trained, for example, birds chirping with the text birds chirping, did this on a scale, and now the model is very good at understanding and correlating text with audio. So you can take a look at that model and do the same thing to achieve this for audio.
This is great. Thank you for that answer. Varun says thank you for the answer as well. It was insightful for them. Yeah, so overall, I'd like to say thank you for giving this talk. It's been great. Personally, I've learned a lot. Also, do you have like social media where we can reach you in case someone is curious? Feel free to share.
Yeah, definitely. So you can reach me on Twitter. My DMs are open at this handle _Rajhans. Yeah, always open to talk about anything Elixir. Yeah. Thank you so much for having me.
Was this worth your time? Hope so. Please subscribe to stay in the loop for more of this content. In case of any queries or suggestions, feel free to hit us up on Twitter. We'd like to extend a warm welcome to ElixirconfAfric 2024. And here's the best part about this one. It'll be an in-person event. What a good excuse to come to Kenya. Again, we're super grateful for helping make this a success, and definitely looking forward to seeing you in the next one. Cheers!